Welcome to this explainer on behalf of Forge College. Today, we're heading straight into the high-performance engineering garage. We're going to build a custom racing engine specifically for your Solana programs. You know, if you've been following along with our advanced Solana program structures track, you already understand that in Web3, and especially on Solana, every single byte of memory and every compute unit absolutely counts. So today, we're getting our hands dirty. We'll be implementing advanced data structures and running some incredibly rigorous performance checks to build what we are calling the PackedVec engine. Okay, so here's our blueprint for the lab today. We'll start with a quick welcome to the lab, then move into designing the PackedVec. After that, we'll talk about handling unsafe Rust carefully, followed by benchmarking with criterion. Then we'll do some strict memory safety inspections, and finally wrap up the build. All right, let's kick things off with Section 1. Welcome to the lab, from debugging to building.
So in our last session on debugging concurrency and unsafe patterns, we successfully patched up some pretty dangerous engine leaks. Now, we're taking off the training wheels entirely to build for pure, unadulterated speed. We're basically making a major trade-off today. We are trading the ergonomic safety of Rust standard vector, which is fantastic, right? It handles ownership beautifully, kind of like your ultra-reliable family sedan. We're trading that for the PackedVec. We are essentially ripping out the back seats, tearing out the air conditioning, and manually managing our memory allocations to construct a lightweight racing engine that is 100% optimized for Solana's tight compute limits.
Moving right along to Section 2, designing the PackedVec, the engineering blueprint.
Building this bad boy involves 4 very precise steps. First, we have to set up the project's skeleton, establishing our workspace and bringing in Criterion as our main testing tool. Second is the core implementation. This is where we ditch those standard abstractions and build a manually managed byte buffer. We're talking raw bytes here, which gives us total control over alignment and lets us avoid any of those pesky per-element headers. Step 3, we build a benchmark harness so we can actually measure our claims. And fourth, we run it and iterate, tweaking things like our memory growth strategy until it's perfect.
Now, while we're calculating our element sizes for this manual byte buffer, we inevitably crash into a really fascinating quirk of Rust, zero-sized types, or ZSTs. These are exactly what they sound like, types that literally take up zero memory space. When you're manually calculating byte offsets, you really have to watch out for these. It's a bit like trying to install invisible car parts, right? If you try to divide a buffer by 0 bytes, your entire program is going to panic. So you absolutely need to create a special case for ZSTs in your element size logic to keep the engine running smoothly.
Section 3. Handling unsafe Rust carefully. Welding without a mask? To pull off this ultra-compact layout, we have to handle unsafe Rust. Think of it this way. If safe Rust is like driving a car with automatic emergency braking, unsafe Rust is like welding without a mask if you don't know exactly what you're doing. But here's the thing. Using unsafe doesn't mean your code is inherently broken or bad. It just means the compiler is handing you the safety checklist, basically saying, hey, I can no longer guarantee this is safe, so this is entirely on you. We compute a byte offset and use unsafe to execute pointer arithmetic and call ptr.write to put the value directly into our destination pointer. And when our vector is finally destroyed, we manually call ptr.dropInPlace so all those resources are properly cleaned up.
Because of all this, there is a golden rule we have to follow. Keep your unsafe code localized to tiny blocks so that it's easy to audit and reason about. You really want to confine it to the absolute smallest possible API surface. Think of it like wrapping it in a safe, protective exterior shield. And most importantly, you have to document the invariants. Those are the strict, unbreakable rules that must be followed for that unsafe code to run without completely crashing your program.
All right, Section 4, benchmarking with criterion, the dyno test.
Let's be real. Anyone can just claim their code is fast. But how do we actually prove this custom structure is faster than Rust's highly optimized standard library? Well, benchmarks are evidence, not proof. We use a rigorous benchmark harness with a really powerful tool called criterion. This allows us to measure our throughput, track the exact number of times we allocate memory, and monitor our peak memory usage across multiple different iterations.
To get a truly complete picture of our engine's performance, we have to test across several parameters. First, we test different element types, comparing a simple primitive like a U64 against a custom 16-byte struct. We do this to see exactly how non-trivial drop behaviors affect our performance. Next, we tweak the initial capacity, testing 0, 1,000, and 10,000 elements
to measure the hidden costs of buffer reallocations. And finally, we vary the workload, testing heavy pushes, random access gets, and contiguous iteration. By running all these variations, we gather hard, concrete evidence of our performance trade-offs. For example, you might find that your PackedVec is blazing fast for tight iteration, but requires a very specific growth strategy to handle heavy pushes efficiently.
Moving into Section 5, Strict Memory Safety Inspections, Passing the Audit. A blazing fast racing engine is completely useless to us if it just explodes on the track, right? To ensure we don't have overlapping writes, pointer alignment issues, or nasty use after free bugs, we rely heavily on Cargo Miri. Think of Miri as our strict, uncompromising mechanical inspector. It's an experimental tool that actively watches for memory safety violations that the standard compiler might just gloss right over when you're using unsafe. We run this tool alongside a strict memorysafety.md file where we meticulously document every single invariant our code relies on.
Before this code is allowed to leave the garage, it absolutely must pass our strict acceptance criteria checklist. First, it has to compile without any undefined behavior warnings. Second, it must successfully run the benchmark harness and compare itself against the standard Vec. Third, it must pass those rigorous miri memory safety checks we just talked about. Fourth, all unsafe preconditions must be documented. And finally, you have to note your concurrency strategies, like, is this structure strictly single-threaded, or how exactly do we wrap it for safe concurrent reads? Only when every single one of those boxes is checked is it truly safe for on-chain consumption.
And finally, Section 6, Wrapping up the build, the finish line.
So we didn't just write fast code today. We actually proved it was fast and safe through localized unsafety, strict testing, and meticulous documentation. And this leads us directly into our next level of learning. How will these compact data structures impact cross-account memory layouts in our next lesson on foundations of program architecture? The core decisions we made today about memory layout will completely dictate how efficiently our programs span across Solana accounts. So, as you gather your benchmark outputs for that next architectural challenge, remember to visit forge.college to dive even deeper into this subject and to access a massive wealth of other Web3 related topics. Thank you so much for joining this explainer by Forge College, and I will see you in the next build.